Welcome to another Mr. Paul video. Today we're discussing 13.2 and 13.3. We're putting two together today, and we're discussing the volume of cones and the volume of spheres. Now, I felt comfortable putting these two together because there's a lot of similarities between cones and spheres. As a matter of fact, there's a lot of similarity between all the shapes we've been learning. So let's revisit a shape that we should know, the cylinder. And there's some aspects of the cylinder that we know, such as the distance from the top to the bottom is the height. And then it's a stack of circles. But the circle at the top and at the bottom, it has a distance all the way across called a diameter, and then a distance that's halfway across called a radius. And we're going to be building on that today. And we're going to introduce the new shape, okay? But first, we're going to look at the cylinder, okay? You'll notice that this cylinder has a hole in it. It has a circle type on the top and on the bottom. And it looks just like this cylinder, except for it's down something like this, okay? So we're talking about the same shape. And what we've been calculating the entire time is its volume. Now, I brought some water with me today in this fancy jug, and I'm going to pour the water into this particular cylinder, okay? And this water is what we've been calculating. This water is going to represent what we've been calculating, okay? The amount of water that this shape, this cylinder can hold is the volume of the cylinder. So what we've been calculating is how much water can this hold? If this was a can of soda, we're calculating how much soda this is. Now, we're going to take that same idea, okay, with the water, and we are going to compare it to another shape that we're going to be learning called a cone. Now, a cone has a lot of similarities to a cylinder, okay? You'll notice that both the bottoms, right, or the tops, whichever way you're looking at it, are both circles. I don't know if you can see that on the camera, but they're both circles. And one major difference is the other side, where one side comes to a point and the other side does not, okay? So one side's pointed, one side's not. Cones are things like you dump some ice cream in there and then you enjoy some ice cream, and an ice cream cone. Or you might see them on the road with there's like a hole at the top. There might be a base on it, but they're orange and they're called road cones. Cones are also made like party hats, okay? This particular shape does have something in common with the cylinder. As you can see, these cone and this cylinder have the same size as far as height goes, okay? You'll also know that they both have the exact same size circle when talking about the top of the cone and the top of the cylinder. And we're going to be comparing and contrasting the volumes of each of these shapes. And we want to know, okay, which one holds more? Go ahead and pause the video, and if you have a guess, and try and figure out which one do you think would hold more, the cone or the cylinder? If you pause the video and you took a guess, let's figure it out. So let's imagine that these have the same. If these held the same volume, they should be able to hold the same amount of water. If I fill this with water and I go to pour it into my cone, there should be no water left in the cylinder, and all of the water would be transferred to the cone if they held the same amount. So that's our first thing that we're going to explore today. So I'm going to fill my cylinder with water. Okay, I'm going to try and get it as close to the top here without making a huge mess. But it's almost full. You can see how it's almost full, right? The top of the water right there. Okay, and I'm going to pour this water into the cone. Okay, so I pour the water into the cone, and I'm going to get the cone as full as I can. And you'll see I quickly run out of room. The cone is now full of water, but I still have plenty of water in my cylinder. So what that tells me is that obviously this volume is not as big as this. Okay, it's not as big as the cylinder. But maybe the way that I can think about it is, instead of pouring water from the cylinder into from the cone into the cylinder, what if I was to pour water from the cone into the cylinder instead of the cylinder into the cone? So I'm going to move the camera to a place where we can see it. So don't get shell-shocked with the videos, okay? And what we're going to be doing is watching and seeing how many cones it would take to fill up our cylinder. Okay, so here's our cylinder here. Okay, here's our cylinder. And I'm going to try and do my best to show you. I'll move this over there. And I'm going to do my best to show you how many of these cones should it take to fill this up to the top. Now, this is another opportunity for you to pause your video and check it out. How many of these cones do you think, when I fill it with water and I dump it into the cylinder, how many do you think it would take to fill it to the top? I think it's time to find out. So I'm going to fill this up as full as possible here without making a mess. Okay, and I'm trying to get it pretty full here. And this will represent the volume of one cone. One cone. As you can see, it's pretty full to the top. And I'm going to take this cone and I'm going to pour it into my cylinder. And this will represent one cone of volume fills up that much of a cylinder. And now my second cone of volume. Okay, fill it to the top. Pour it in. All right, and one more. Looks like it might take one more. Okay. Now, as you can see, that this cone, I had to fill it up 3 times to make this cylinder full. There is just a hair difference with the top because I didn't want to spill. But as you can see, the water's filled to the top. Okay? Now, what does this all mean? What does this all mean? Well, let's set up the camera and think about it. Well, when comparing the two volumes together, we were talking about two separate shapes. Mainly, we were talking about the cylinder and the cone. And we're trying to compare them, and we measure them with water. So, excuse me, when we were combining the cone into the cylinder, it took 3 cones to fill up one cylinder. So we could say that this cylinder is 3 times as large as a cone. Okay? But in referencing the cone, how would we compare that to the cylinder? Do you get what I'm saying? I can say that a cylinder is 3 times the size of a cone, or I can say the cone is what compared to the cylinder. And that's what we're going to be exploring today. So when creating a cone, this is our second shape, a cone, we're going to make the same circle like we did at the top. Okay? And then we're going to make like a V underneath. Okay, and this will be a cone. And there's a lot of similarities between cones and cylinders. For example, the distance from here to here is still called the height. And the distance on the circle part from the middle to the outside edge is still called the radius. But it's not called the radius of the circle. It's not called the radius of the cylinder. It's called the radius of the cone. And also equally as true, the distance all the way across the circle part, just like the cylinder, this piece here, this distance all the way across is called the diameter. And once again, the same is still true, that the radius is half of the diameter. Okay? Now, what about the volume? Okay, what about the volume? So the cone has a volume, okay? It holds a certain amount of stuff. And I know it's related to the size of the cylinder. So I'm going to write the cylinder's volume first. Pi r squared h. Now, we can think about what we just did with the pouring the water thing. It took 3 cones to fill up 1 cylinder. Okay, so this is 3 times the size of this. But when referencing, okay, how is this size compared to this? This is not 3 times this size. This is 3 times this size. But when I'm talking about how is the cone compared to the cylinder, it is not 3 times, but 1/3 its size. 1/3 its size. Meaning, this is the volume of the cylinder. If I multiply by that by 1/3, I'm going to get 1/3 of this, right? If I was to separate this into 3s. Okay, one of these filled up this amount here. Okay, one of the 3 sections. One cone filled up 1/3 of this. So if this is the volume of the cone, 1/3 of that is what the volume of 1 cone would have filled up. Meaning all of this filled up that piece of the volume of the cylinder. And this is where the formula comes from. And it's equally as easy to use once we know what we're looking for and we can punch stuff into a calculator as the cylinder is. So one common example, let's do an example here. We're going to make a cone. We'll say we have a cone here. And we are going to give a distance here, say of 8. And then we'll give a distance from here to here of, say, 5. And we want to find the volume of this cone. So find the volume, okay, of the cone, Now, the volume of the cone is V equals 1/3 pi r squared. So V equals 1/3 pi r squared h. Well, what information do I know? 1/3, that's a fraction, but it's just a number. It's a number I can input into my calculator. So I'm going to leave that alone. I don't need to understand what that is. Pi, it's a symbol, but it represents 3.14. And I like dealing with the number instead of the symbol. The R stands for radius. Remember, the letter R, lowercase r, is your radius. So the radius of my cone is 5. So this is 5. Don't forget the squared. And then h is height. Remember, the h, lowercase h, is how you represent height. So the height of this cone is 8. Now the rest is just a matter of understanding what to put into a calculator. The volume is equal to 1/3 times pi, which is 3.14. And then I'm going to multiply that by 5 squared. So 5 squared. And then times that by 8. Okay? The rest is a calculator. And I just have to grab my calculator here. Okay? I'm going to grab my calculator. And to put fractions in, I'm just going to press the buttons. That 1 divided by 3. And then I'm going to multiply the rest. So I'm going to press 1 divided by 3. That takes care of the 1/3. And then pressing times 3.14. Then times it again, right? Times it again by 5 squared. 5 squared is 5 times 5. So I'm going to go 5 times 5. So I have 1/3 times 3.14 times 5 times 5, right? There's 2 multiples of 5. And then times that by 8. Times 8 equals 209.333333, repeating. You guys can barely see that. Hopefully you can see that. 209.33 repeating. Now, it's okay to simplify that. 209.33. And we can stop after 2 places after the decimal. Okay? It's not going to be a rounding error. We've already rounded once with the pi, so it's going to be okay. And the volume of this cone is 209.33. Now, what about the other shape? We've discussed cones. Let's talk about spheres. So if you are completely comfortable with the cone, I'm going to erase it. So pause the video and copy it down if you need it. I'm going to erase this information, and I'm going to give you some information on the sphere. The sphere. Let me erase this really quick. Now, hopefully, we all understand and have seen spheres before, okay? Spheres are things like basketballs. Basketball is a type of sphere. Baseballs are types of spheres. Anything that's round, basically, in a three-dimensional world is a sphere. Now, this sphere, I chose this particular one because of what we're trying to illustrate when we draw the picture. You'll notice that all basketballs have these lines, right? These lines. What we're going to be doing is creating this middle line, okay? This line down the middle. We're going to be creating this middle line to kind of illustrate that when we draw it on the board, we're kind of showing this middle line to show that this object looks 3D, but when we draw it on the board, it might not, okay? So the way you draw a sphere on paper looks like this. This is a sphere, okay? And it is a circle. You're going to make a circle like this. And yes, it's incredibly hard to draw a perfect circle, but we do our best. And we're going to create a middle line. So what we're going to do is we're going to start at one side, and then we're going to make a bow, right? Something that bends down, like the bottom half of this, right? We're trying to recreate this circle, but in the middle. Okay, so making a bow down here, and then we're continuing on the top, but instead of making it a solid line, we're making a dotted line. Okay, we're making a dotted line. Now, in mathematics, a dotted line is used to represent the pieces of the item that you can't see. So, for example, you can see the front side of this, okay? But when I grab the basketball, obviously, to make it look like, let's see if I can make it look like that. Okay, to make it look like this, you can see this line, okay? You can see that line down here, but you can't see the backside. But to be able to see inside of the ball, we have to show that there is a backside to the ball, and anything that's in dashes lets the reader know, okay, there's a backside to it, and it looks like the dashed thing, like the dotted thing. Okay, there are important things that we know about the sphere. Just like a circle, okay, remember a circle has a radius to any outside edge. The sphere has the same. The distance from the very center of the basketball, the very center of this basketball, like inside where the air is what we're talking about, the very center, to any outside edge, meaning I can go to this outside edge, right? This is like that front, or I can go to the outside edge in the back, or I can go to the outside edge in the front. The distance from the center of the ball to any outside edge is known as its radius. Okay? There is no height. There's nothing else after that. And the sphere has a volume as well, but it's nothing like the other ones. As a matter of fact, I think it's a little bit easier, but it is a little bit different. The volume of a sphere is 4/3 pi r cubed. More importantly, cubed. You'll notice that this radius is not being squared anymore. This radius is not being squared. It's now to the third power. And this 4/3 pi r cubed is how you calculate the volume of a sphere. And why I think it's easier, you'll notice that yes, I do have to multiply by one extra radius, but I don't have to find a height. The height is irrelevant. So when finding the volume of a sphere, literally, we only need one piece of information. So here's our example. Okay? We have a circle, and then we have a sphere. And I'm going to say that the center to this outside edge, remember this is more like the top of the ball, that's the front of the ball. I'm going to say the distance is 3. Okay, the radius is 3. Remember, the distance from the center to any outside edge is 3. So when calculating the volume of the sphere, find the volume. V equals 4/3 pi r cubed. Remember the cubed. Remember the cubed. There's only one piece of information that I need, and it's the radius. And I know that the radius is 3. This is the radius. So I know what pi is. I can replace that by 3.14, and that's my personal preference. I don't like dealing with symbols. And the radius is 3. So the volume is equal to 4/3 times 3.14 times 3 to the third power. The rest is for my calculator to work out. Okay, so we have a calculator, and just like we did before, we're going to put a fraction into a calculator, okay, by pressing 4 divided by 3. So we're going to start with that, 4 divided by 3. Then we're going to multiply, right? These are multiplied by 3.14. So times 3.14. And then times that by 3 to the third. Now, 3 to the third is multiplying by 3 times 3 times 3, right? There's 3 threes. So 4/3 times 3.14 times 3 once, times 3 a second time, and times 3 a third time. Remember, it's 3 to the third power equals 113.04. 113.04. So the volume of this sphere is 113.04. There's a lot of similarities between spheres and cylinders and cones. Okay? The major trouble points, as we said, are identifying what you got, knowing what you need, and once again, being able to use the devices at our disposal. That is it for today's video. I hope these help. Peace.